In the last section of this part on dynamic, on divide and conquer algorithms, I want to show you just very briefly two other examples where you can use divide and conquer, but we won't go into much detail. This is basically just teasering what's possible. But it's two more cute problems, which maybe you enjoy as puzzles, even if we don't do them in detail. The first one is the majority problem. So a new problem, time to wake up again. You're given an array of objects, and your task is to find, if it exists, an object that occurs more than half of the time. So a simple majority in political terms, but it may not exist, right? You may have elements where there's too many different elements and no one is in the majority. But if there's an element in the majority, you're supposed to report it. Let's see what we can do without much sophistication. You can go through the array and try every element and check if it is a majority. How do you do this check? Well, you compare it with every other element and keep a count of how often it came out equal. So it's just count the number of j's so that ai was equal to aj. Well, and if that count is bigger than n-half, then it is a majority. And maybe stating the obvious, if you have one majority that you found, you can stop because there can only be one majority. Right? It's more than half of the elements, so there can't be more than one of those. The algorithm is still not so great because in the worst case, it might need n-squared time. In particular, if you have an input where you don't have a majority, you have to keep going until you tried every element to prove that there is no majority. Okay, so even if your output is just, no, there is none, a correct algorithm is supposed to have implicitly proven that that's correct. So it can't just say no and keep fingers crossed. Good, so that's the obvious one. There's various ways how we can do better. If you never thought about this problem, it's kind of a shame. I feel with you that I'm spoiling it before I've given you a fair chance to think about it. But there's many other problems for you to think about, so I can point you to more. Let's try to apply the divide and conquer approach to this. And the reasoning is, suppose this array has a majority. Well, then it's present in more than half of the positions. That means if I look at the halves of A, if I just cut them in the middle, merge sort style, if there's n-half elements, at least n-half positions where this majority occurs, they must be somewhere, right? So it has to be the majority in either the left or the right side, or maybe even in both. There's just not enough places to hide it otherwise. So in the worst case, you have an equal split, say roughly n4 and n4 plus 1. But then it would be a majority in this right part. So it's worth pointing out, majority means strictly more than n-half. It's not good enough if you have an option that's half the people. It must be half plus 1. Good. So that's the observation. If there's a majority, then I can cut the array in two parts. And if there's a majority in the overall thing, it's the majority of the left part or the majority of the right part, and they could turn out equal. If both of these parts don't have a majority, then I'll have to think about it probably. So we recurse on the left and the right half, and that comes back with some candidate. So what are the options? So we can have, from the left, we can either have some value x, or it says there is no majority. And from the right, we can have a value y or not a majority. If either of the two says none, if both say none, then there's no majority overall by this argument. Okay. Right, as proof by contradiction, if there was an overall majority, then it would have been the majority in either the left or the right side at least. So if both are none, we just return none. And otherwise, we have a candidate or two. So the check is, again, as before, we compare it with every other element, but we're only doing this with at most two elements now, two candidates. So that has linear time. And if you write down the recursion, you'll see it's exactly as in merge sort. So the overall cost for this, in the worst case, we'll have to do the recursion on the left and the right side. So assuming that things work out nicely and we don't have to round, so assuming n is a power of 2. Then we have two recursive calls on half the size, and we add something that's linear in n from checking the candidates. And that's precisely the shape that we've had for merge sort, and so the solution is of the same order of magnitude. Again, I want to stress this many more times. N log n and n squared, if you just look at the functions, maybe it doesn't seem like a big deal, but it's a huge deal. N squared is so much slower than n log n in most cases. All right. Now, it turns out in this case, you can do much, much better if you just throw divide and conquer overboard. So this is an algorithm that doesn't actually have any justification to be in this unit. It's not about sorting and it's not about divide and conquer, but it's so cute and cool that I want to show it anyways. And it's it has a nice analogy. I'll come back to that, to these two guys. It's the following algorithm. You start out with some candidate for the majority, but initially you have no idea, so you just set arbitrarily this to some value. Sorry, access the candidate. C is a counter. You start with the counter 0 and you don't have a candidate. If the counter is currently 0, then you take the next element that you're looking at and say, maybe this is my majority. And you said, I've seen that once from now on. If the counter is not already 0, so you have some candidate from before and you've seen it a certain number of times, then you update the count. Either if the element is occurring again, you increment the counter, but if it's a different element, you decrement it. Okay. And the claim is, once this has done, it will always return an element. It always returns x. So that's a candidate for the majority, but it may not be the majority. You need another check for one element. Okay? That's this part. But the cool thing is, if that procedure gives you something and it's not a majority, there is no majority. And the reason to see this is where these two guys come in. You can imagine there's a fight of different parties, and they fight in duels. And whenever two people meet, they have a gunfight, and they actually both die. It's a gruesome world. So what you do here is access your current leader of the underworld. And if someone else comes along and they're from the same gang, they just join the fighting group. But if it's someone else, they have a duel and they both die. And if you ever reach the point that nobody's currently staking the claim, then whoever comes next becomes the current leader. Now, if you have a majority, there will always be one from that gang standing after the duels. That's the part that you have to prove for this one. Again, it's not really about divide and conquer, so I feel it's a bit it's a bit outside of this thing, but it's such a cute algorithm that I wanted to show it. But again, this is for fun for you. We don't have to obsess about it too much. Very briefly on the second example, second of the other divide and conquer problems. And for this one, I'll leave it with the claim. This is something that sometimes you do in some algorithms classes, but it's a bit of a more advanced thing. So I just want to show you that you can do more fancy things with divide and conquer. But we won't do the details. But I want to define the problem. So this time, it's not just numbers, but it's points in the plane. So two-dimensional points. You're given a list of those points, and they each have an x and a y coordinate. That's how they're Cartesian coordinates. Okay. And your task is to find two of those points that are closest in standard distance, Euclidean distance. Okay. You can imagine how this could be a useful problem in various applications where, I don't know, the points could be things on the map, or you can cook up various things where this pops up as a sub-problem. The naive solution would be look at every pair of points, compute the distance, and keep track of the minimum that you've seen over the whole point of the whole course. And again, that would be possible, but it's quadratic time. So if you have thousands of points, that won't be efficient enough. And with divide and conquer, you can do it in n log n time. The main idea is that you divide, if all those points lie in such a rectangle, you cut that in half, and you recurse on the left and right side. So you find the median in x coordinates, so that half of the points are left and half are right. So I guess this is a bit misleading. The line doesn't need to be in the middle, but half of the points are left, half of the points are right. How do you find the median? Haha, we've just seen in the previous section, right? You can do that in linear time, worst case even. Okay. Then you recurse on those two parts, and then you get back two pairs of closest points. Maybe two here. And okay, let's say the other two are here. So you get to these two candidates, and you can compute which one is closer to each other. But you're not done, because there could be points that are just around the dividing line. So they're split by, okay, maybe a little bit more careful. The point is that the point is on either side of the line. So these two might be closer, but neither of the two half recursive calls would have seen the pair, because they each got just one of them. But the trick is that you can, you know that you have this distance already. So these points, I mean, they cannot look like that. They cannot be so far away. This would not be a viable candidate. So instead, you can find some range around this line, and only the points in that range are potentially candidates for being closest. And you can further trim down how many of those there are. But I'll stop here and just tell you, you can look this up. You don't need to know. I just wanted to show this as another example what divide and conquer can do, beyond the simple sorting algorithms. But that's the key idea. With enough time, you can work out the version that has a log squared in the running time, I think.